So if there's nothing specific anybody wants to discuss, what I thought I would do was just go through a few examples of applications of interatomic potentials. Assuming you've got all the notes and the recordings, I didn't think there was much point going through the recordings again. So I'm just going to show you some examples. So these examples I've chosen these because they're all quite complex simulations, either long time scales or very large simulation cells. And there's a selection of a number of different types of interatomic potentials that we're over in the lectures. So there's a bit of a variety. So the first one is actually about complex ferroelectrics, and this represents an application using Buckingham potentials for ionic crystals. So these are basically ferroelectrics, and these simulations were done by two students of mine just a few years ago. The second one I wanted to show a large biological simulation, and of course a topical thing these days is the SARS-CoV-2 virus. So I searched the literature and found what I thought was quite an impressive simulation of this virus. Just notice the pictures come back to front. Never mind. So that's how I'm going to talk a little bit about these simulations, even though I've not been involved in them. I thought they were quite a good example of how these classical potentials can be used for very large simulations of quite an important application. And the final one, I wanted to show an example of the reacts SF potentials, because these are the most complicated ones we talked about. So this was done by one of the original developers of the reacts SF potential, Van Duem, and that's a recent simulations from last year of graphene growth in silicon carbide. So again, quite topical. So moving on to the first example, this is for a ferroelectric, quite a complex ferroelectric. It's a lead, zirconium, titanium oxide ferroelectric, and that's often shortened to PZT. So this is a ferroelectric that's actually very widely used for industrial applications, such as sensors, transducers, and capacitors. It's particularly important because it's got a very high piezoelectric response. So with a very small electric field, you get a very large strain. And a very large dipole would be induced across the cell with a small strain. So it's very responsive, and that means you can use much less of the material. So this project was funded by NPL because they were interested in these applications. And they funded two students about 2016. So PZT is a solid solution of PTO, which is lead titanium oxide, and PZO, which is lead zirconium oxide. So it's quite complicated, and this is one of the reasons that we really do need to have classical potentials, because it's a solid solution. It's actually a disordered material. Therefore, if we're going to simulate it, we actually need very large unit cells. Also, if you're going to simulate ferroelectrics at all, the important thing about these materials is basically domain walls. What gives us their functionality is domain walls between two different domains of different polarization. So again, any sort of defect, any wall-like defect, takes extremely large unit cells. Therefore, the only way of simulating these is with classical potentials. So there's a solid solution, and like many of these ferroelectric oxides, it actually has a perovskite crystal structure, which is shown in the diagram down here. Let me see if I can find my pointer. There's a pointer. So it's a ferroelectric below a certain critical temperature, that above the critical temperature, it's paraelectric. That means above the critical temperature or below critical temperature, there's a net polarization. So the unit cell actually distorts and gives you a polarization. Above the critical temperature, you have a cubic structure. And basically the perovskite structure means you have the lead ions on the corner of the cube, the oxygen ions in the center of the face, and either they're titanium or zirconium ions in the center of the cube. And that's a cubic above Tc. So no dipole moment across the cell, no polarization. Below Pc, the critical temperature, the unit cell distorts. And that means that it becomes tetragonal. But not only that, the central ion, titanium or zirconium, goes off center. So you can see you have a net dipole moment or polarization across the cell. So this will happen whether or not you apply an electric field. If you apply an electric field, this distortion actually increases, therefore the polarization increases. So that's basically ferroelectric, and that's what we would like to model using classical potentials. So one of the interesting things about this material is its structural phase diagram, and I've shown a schematic of that here. So if it's pure zirconium, no titanium, you get antiferroelectric rhombohedral crusts. And as you increase the amount of zirconium, you get a ferroelectric. However, it's still a rhombohedral structure. When you get to more than 50% of titanium, then you actually get a tetragonal crystal structure as shown here. And it's again ferroelectric below the critical temperature. If you increase the temperature, it becomes cubic, therefore it's paraelectric, as you get no net polarization. Where the technology comes in is actually in the central region, round about 50% titanium. This is called the morphotropic phase boundary, and most of the interesting applications use this material. And that's because it's got a very large piezoelectric response. Therefore, if you use a very small electric field, you get a very relatively large polarization. Therefore, it's very sensitive for all the applications that ferroelectrics are used for. So this is what we would like to be able to reproduce this type of behavior using classical potentials. Clearly, that's quite challenging. So it's an oxide ionic crystal. So then with natural potential to use would be the bucking potential. I've shown it here. So basically you have your attractive van der Waals type interaction and your repulsive wall, this exponential term, with 3 parameters. Obviously it's ionic crystal, so we also have the Coulomb interaction. And because it's a ferroelectric, obviously the polarization effects are really important. So if you want to model these, you have to be able to model the polarization very, very accurately. So we need to use the shell model, as I discussed in lectures. So we have a core shell potential. We assign the core a positive charge, QC, and the shell a negative charge. And we attach these 2 things with a spring. So usually when you do a shell model, you have a harmonic spring. Therefore, you've got a spring constant and that's proportional to the R squared. So the energy separation is proportional to the square of the separation. This doesn't really work very well in these potentials because they're so polarizable that you can get very large displacements between your core and your cell. So you need to add another term. So it's an anharmonic spring, and you add a quartic term as well. But basically, the shell model will capture the polarization of the ions that you want to polarize. So we're going to have a bucking potential, we're going to have a Coulomb interaction, and a core shell interaction. So we're going to go about fitting the potential. This is a very challenging, and quite often, well, for any potentials, it's quite challenging. Quite often, parameter fitting is actually described as an art rather than a science. You'll hear more about this in next week's lectures, but I just wanted to summarize here how Oliver went about making these potentials. He used gulp, which I should think most of you will be familiar with, and very standard molecular dynamics and ab initio code. So, and it started with, you have to choose somewhere to start. You need an initial set of parameters, and there are a good set of parameters for lead titanium oxide already. So started with those from an existing potential that works very well for the PTU structure. Then you used DFT parameters for PZO. As I said before, this is an antiferroelectric crystal, and So you use this, fitted that to the rhombohedral and the cubic phases. And then if you fit the charges calculated in DFT, the lattice parameters, and all the atomic positions simultaneously, but didn't change the lead oxygen or oxygen parameters. So after that was done, then they reparameterized to fit to the DFT calculated parameters of other structures, for example, the tetragonal and cubic phases of PTO, the orthorhombic and cubic phases of PZO, and the tetragonal phase of P, so the mixed phase, so a mixture of 50% zirconium and 50% titanium. So after that was done in a satisfactory way, they finally modified the parameters again to fit to the Bohm effective charges to calculate the polarization, the elastic constants, and the piezoelectric coefficients, all of which were obtained with DFT. So everything was fit to DFT rather than to experimental parameters, which would have been another option. But of course, these are not really known for all of these different phases. So we did everything to DFT. So again, just emphasizing what a tricky thing this is to be able to fit potentials. It's an iterative process. So you have to choose the weights of each of your parameters you want to fit to. So some things may be more important to get right than others. You're never going to get everything exactly right when you're using interatomic potentials. So you want to choose which are most important parameters that you want to get right, most important observable. And what is the acceptable error tolerance for these? You choose these to start with, then you plug these into Gulp and you do an optimization, and you'll find that because of this, you'll get some errors in all your parameters. So you check, are these acceptable below the target? If not, you go around the loop again, adjusting the weight until you find that your errors are acceptable. And then you've got a set of parameters for your interatomic potentials that you think will fit everything nicely. However, you've only done these to the ground state properties. You haven't put temperature in there yet. So you will want to test them using molecular dynamics. We'll put in a finite temperature. So if this works, and if you don't find any surprising behavior, nothing crashes, doesn't do anything strange, then you've got a set of potentials that hopefully you can work with and do your simulations with. However, if something odd does happen, if the simulations crash or it doesn't behave the way you expect when you do finite temperature simulations, then you have to go around the loop again. So basically there are two loops, an inner loop and an outer loop. And you're effectively starting again when you do go around this loop the second time, shake the thing up and you fall into a different minimum. So after you've done all this and got a set of potentials that you're happy with, and this is the case that we had for these, so I don't really, the numbers aren't particularly important, just to say that these are the Buckingham potentials, the parameters that worked. And then each of the ions has a core and shell charge and two parameters for the core shell interactions. And I want to point out here that look at these very large charges for the lead and zirconium ion. But if you add the core and shell charge together, of course, they're quite small. They're more like +1.5 instead of 10, 11. Also, you can see that very small spring constants for the lead and oxygen. So that's actually demonstrating that these are very polarizable ions. So that will give you the properties of your potentials. So those are the interaction potentials that we can go ahead with. So do they work? Well, as I said at the beginning, one of the things I really wanted to get out of this was actually the structural phase diagram. So we had different phases depending on the amount of titanium or zirconium in our solid solution. So let's look at B. So B is PTO, so pure titanium. I already know that this is tetragonal. So how we actually set this up was make very large unit cells and run very long simulations. So these are molecular dynamic simulations, NPT or NST really. So you basically, you keep the temperature constant, but you let the unit cell relax and all the ions in the unit cell relax, and you let all the lattice parameters, so you're not constraining any of the lattice parameters, you're not constraining the crystal structure. So from this, you can actually get all the individual lattice parameters, A, B, and C, and you could get the angle between all these lattice parameters. And you want to do this for many different temperatures. So you can see all these dots are individual simulations, or quite long simulations, increasing the temperature. So it starts with the A and B parameters the same, and C bigger. So all the angles here plotted, all 90 degrees. So you've got a trigonal unit cell. And as you increase the temperature, these individual simulations, so you get the lattice parameters for each of these individual simulations, increase the temperature, and gradually the A and B becomes closer to the C parameter. And at a particular temperature, around about, I think it's 570 degrees Kelvin, they converge. So this is a signal. You've got a ferroelectric phase transition that goes from ferroelectric to paraelectric at this point. And now your A, B, and C parameters are all the same. So you've got a cubic crystal structure, and they're still all 90 degrees. So this is you've got your cubic crystal structure for this particular your PTO, and you've got a transition, ferroelectric transition temperature of about 570. So then looking at C, this is the 50% zirconium and 50% titanium. So this is basically a random structure. In this case, it's not an ordered structure. You've distributed your zirconium and titanium atoms at random throughout your structure, so into a large unit cell. And remember, in our phase diagram, this was actually monoclinic. So it was in the border between the tetragonal and the orthorhombic crystals. So it was actually monoclinic. So there was some competition between the two different phases. And you can see that here you've got different A, B, and C parameters. And as they increase the temperature, they change, but they're always quite different. And the angles are not 90 degrees anymore. So this is a signal that you've got a monoclinic crystal structure. And again, they all come together around about 400 Kelvin, and that signals a transition to the ferroelectric, to the paraelectric phase. And then that's now cubic, because A, B, and C are now all the same. The angles are all 90 degrees. So the fourth diagram here is actually the polarization. So if you want to have, you can also look at the polarization of your crystal as you increase the temperature. And you can see you start with PTO, your polarization is quite high. So this is no electric field, but you get quite a high polarization. Increase the temperature, and it drops suddenly to zero, around about 600, which is signaling your transition to the paraelectric phase, where you actually get no net polarization. The same thing for PZT, pure zirconium alloy, and it falls at a lower temperature. And that's when we showed the phase diagram before. Going back to that, you can see that it's got a lower transition temperature for PZO than PTO. So that's what this is showing you in the polarization curve. And the PZ, that was the 50% one. You can see that there's no polarization for PZO, the pure zirconium, and that's because we now have an antiferroelectric. So the polarization and neighboring unit cells are actually opposite. Just like an antiferromagnet, the antiferroelectric polarization is actually zero, because the moments of the neighboring cells cancel out. And that's what we see here. So it looks like the parameters of our potential, actually, the parameters of potential did a very good job in doing our structural phase diagram, which is one of the aims of that. And once we've got the potentials, we can do lots of other things with it. And I just showed you one example here. This is actually looking at very thin films of PTO. So these are actually very important from a technological perspective, because people are quite interested in making very thin ferroelectric films for things like memory devices. and they've got very interesting domain patterns. So the nice thing about these types of simulations is we have all the individual parameters for all the unit cells. So we know what the individual polarization for every unit cell in our simulation is. So these can be shown by different ways in terms of our visualization. So in this case, you can see little arrows on your, which show actually the direction of the polarization, but the colors give you more information because they show you the magnitude. So if you can see dark blue, that means you've got a strong polarization, and the deep yellow is also strong polarization, but the arrows are in different direction. So in this case, what we're examining here is what the polarization does, are basically domain patterns in these very small, thin films. So they're very thin films, nanoscale films of this PTO. And you can see that you put them under different strain, and the domain patterns actually changes. So if you put it on a tensile strain, you can see that the arrows are all actually in plane. They're all parallel to the surfaces. This is the upper surface, and this is the lower surface for your thin film. And all the arrows are parallel to this. So they're in plane strain, but you still get domains. They're pointing in this direction, and then they're pointing in the 90-degree direction, then they're pointing in the other direction again. So you get domain walls and domains in these. However, if you go over to this one, this was tensile strain, so you stretched your film. This was compressive strain. So when you squash it, you can see that the arrows are basically still parallel to the surface at the top and the bottom surfaces, but they're perpendicular in the middle, and they basically change from down to up. And this will do this periodically across your film. So this gives you stripe domains, and this is a perspective view of that. Basically, they're down at this part and they're up at this part. So you get these stripe domains. And what you also get in these simulations, if you increase the temperature, not above the transition temperature, but just below, you get what's called nanobubbles. So they break up, instead of being stripes, you get bubble domains. So this is quite exciting because such things have actually been seen experimentally in thin films that were actually on top of it, the epitaxial strain on them, because they were grown on top of a substrate, which is a slightly different lattice parameter. And they saw quite interesting nanobubble domains. So these simulations actually reproduce that, which is quite nice. So that's basically all I was going to say about these Buckingham potentials. And the main message here is that if you do a lot of work to making quite accurate potentials that will reproduce the physical properties, then you can do very large simulations and very long simulations, and you can reproduce all of the interesting physics you can get in many of these materials. And the example I've shown you was a very complex but very technologically important ferroelectric material. So the second example I wanted to show you was something what I thought was quite topical. So I did a quick search of the literature to find out what had been done for the SARS-CoV-2 virus, and particularly the spike protein. And of course, there's been a huge amount of activity, well, all sorts of research activity, but also useful amount doing classical potentials with the multi-body potential we talked about in the lectures. So there was a lot of different simulations. I had a quick look through, and I saw a lot of them actually have got to do with looking at the effectiveness of drugs binding to these particular proteins. But this was a particularly, I think, interesting simulation because of this time scale and what they were trying to do. So this is a schematic picture of the virus, and the point of interest is actually the fact that these spike proteins, which you hear a lot about in the news, will actually bind to this ACE2 receptor. And it has to bind to this before it can go into the cell, and it has to do this in order to reproduce. So of course, if you can stop it binding to this receptor, this ACE2 enzyme, then you could stop the virus reproducing, and that would be an effective therapy, which is what a lot of these simulations are actually targeting. So you're looking at something that would perhaps bind to the top of this spike proteins to stop it binding to this enzyme, ACE2 enzyme. So this is a zoomed in picture of the spike protein, and you can see that it's surrounded by these dots, and these dots here are actually they're sugars, a type of sugar called glycans, and the purpose of these is to actually hide the virus from your immune system, so it effectively disguises it, camouflages it. But the bit at the top, the bit that actually attaches to ACE2, is actually just isn't surrounded by these proteins. So I've picked this particular simulation from the literature, which was published, I think, in late 2020, mainly because of the size of it. So they felt that really you had to have a realistic environment. So it wasn't much point just looking at the top of this protein itself. You wanted to put the whole protein into a realistic environment, and that means you had to surround it by water, because it obviously behaved quite differently if there's no water in it. And you also have to include this glycan shield, the sugar shield that was camouflages it. So they did all of this, and that meant that in a total simulation they'd got 1.7 million atoms, and they ran your simulation for 3 microseconds, which is a huge amount of time for such a big simulation. But these potentials, these are the multi-body potentials, are actually quite efficient, and lots of these programs are also very efficient, so they could run it for a very long time using a big supercomputer. So the picture B actually shows it with all other glycan, obviously not with the water molecule in there, which are in there, but there's the glycan molecules around as well. So the different colors are different domains of this particular protein. So the RBD is the important bit. It's a receptor binding domain. And then there's this other bit here, which is colored in red, which is the N-terminus domain. And that surrounds the receptor binding domain. So that gives you the N bits of the protein. And then there's the bulk of it and the stalk that goes into the membrane of the virus. So they've run these simulations for a long time, microseconds, which is a very long time for simulation time, as you probably know. And they started in different conformations. So in order to bind to these cells, it has to actually become in an open conformation. So that basically means this, but here, there's 3 parts to it. And if one of the parts, it's actually a trimer that looks 3 bits all stuck together. And if one of the parts of the trimer is actually up, then it's called open, and that's when it effectively binds and effectively into the cell. So they started in different conformations of this open and closed conformation. And what they found, in this particular simulation, is that there was a particular area of this part here, of the N-terminus domain, that the amino acid in this part actually bound quite strongly to the glycans that were actually surrounding it. And because of that, it actually held it in an open conformation, and that helped it to actually bind to the ACE2. So they conjectured that if they actually changed these 2 particular amino acids, if they changed them by mutating them to different amino acids, it would actually change the binding and perhaps the infectivity of the virus. So they did an experiment and actually found that they did get a 40% reduction of the binding to ACE2 by doing alanine mutation of these two particular amino acids. So I thought this was quite interesting, given the discussion now about the different mutations and how they can change how infectious the virus is. So these type of simulations, you'd think in the future, could actually give you a lot of information about infectivity. If you know the mechanism of how things are binding, and you could target particular, you might be able to investigate whether you expect different mutations to be more or less infectious. That's probably not something that's going to be done in the next few months, but over time, such simulations would actually contribute quite a lot to the understanding of this virus. So the third and final example is actually something I wanted to pick up from the REACT-FF force field. So that was the most complicated one we've been discussing. And this was a simulation that was done also last year by Van Duyn, and he was one of the original developers of the REACT-SF force field. So as we said, basically REACT-SF will actually model chemical reactions. So it would model bond breaking and bond forming, and that's its biggest strength really. So what these people wanted to do was actually measure or to model graphene growth in silicon carbide. I'm sure you know graphene has a lot of potential applications, but one of its big problems is it's quite difficult to actually grow large sheets of graphene that don't have too many defects in it, so they would like to be defect free. And one of the ways it's actually grown is using, well, it's usually grown, well, always grown on some sort of substrate, sometimes metal substrates, but also sometimes in silicon carbon substrates. So this study actually investigated different mechanisms of growing these graphene sheets on top of silicon carbide. And it investigated two mechanisms. One was called thermal decomposition. So what that means is actually you would heat up the surface and then you would lose some of the silicons from the surface. If you lose some silicons, then you're left with an excess of carbon atoms. And so how do the carbon atoms actually form or link up in order to make graphene sheets? So that was how they modeled so instead of actually heating it up, because that would actually take too long, they just removed the silicon atoms one by one. I think it was something like a 25 picosecond gap in between removing them. So they would do this, remove it, and then as they removed more and more, you get more and more carbon left on the surface, and that would bond to each other and make a graphene sheet. So it didn't do a full simulations of what would be, because that would be just even too time consuming. The other way that they modeled it was actually CVD. So this is vapor deposition. So there's the vapor here, the gas here, it was acetylene. So two carbons bonded to two hydrogens, and they deposited these on the surface. So these are two separate types of simulations. One was a thermal decomposition, the second was a CVD. And they deposit these gas atoms on the surface, and then see what happens at different temperatures. The gas atoms would lose their hydrogen, and they would split up the carbon, and they would basically grow a graphene film. So the first one, the thermal decomposition, just to show some results from the pic. So you can see that they did this at different temperatures, and these three pictures, A, B, C, actually show what's happening with the same simulations at different temperatures as they removed more and more. So they'd remove one silicon at a time and then let the structure reconstruct. And the gray bits, the colored bits in the top show you carbons and how they've actually bonded. So to make a nice graphene sheet, you'd want to have mainly 6-membered rings. And the 6-membered rings are shown by these colors in the blue. So you can show by looking at the different colors from how they've represented this, just how defective or otherwise what the graphene is in the thing. So at 2000 Kelvin, you can see that there isn't very many 6-membered rings, and you can also see this from the plot. So as I remove different silicon atoms, you can see that the number of 6-membered rings increases, but also there's a number of 5-membered rings and not so much a number of 7. But as you increase the temperature, you can see that you get a better percentage in terms of the 6 to 5 and 7-membered rings. And at 2800 Kelvin, they're doing much better. So this is basically an investigation of the effect of temperature on this thermal decomposition. So this is pointing that higher temperatures are better, but obviously there's a limit to this. If you go too high, then you're going to make more defects. And the second one was actually CVD, and this is where they put the acetylene onto the surface and they did the same strategy. They added them one by one, and this is different snapshots as you add more and more. And you can see again, they've highlighted different structures. The grey again is 6 numbered rings, but they've also highlighted different types of defects. So these are linear chains of 5, 7 rings all linked together. So this is effectively a grain boundary in the graphene. That's how that's signaled. And these 7, 7 by 5 combination of defects as a stone Wales defect. So these are quite well known in terms of graphite and graphene. So they were able to characterize the films not only by the number of rings, but the seed number of defects. So the overall message of this is that they can investigate something quite complicated like growing graphene, and they can actually show, suggest better ways of actually improving this by looking at different temperatures, and not only different temperatures, but different facets, how things were grown on. So it's an interesting simulations. So that's basically the end of my tutorial and showing you different examples. So I want to emphasize the message again, that these carefully parameterized physics-based interatomic potentials can be used to model these very complex materials and also complex processes. And these models are currently inaccessible by any other method. So it's basically worth looking into. So I'll just escape that. I'll stop sharing my screen and we can see if we've got any questions. Screen sharing, stop share. So any comments, questions? Also, I would meant to say if anybody wants us to show anything that they have done with classical potentials, shows any diagrams, that would be very nice to finish off with. Any comments or questions or any examples you want to show? No.
Hey, I've got a question. I'm wondering if you wanted to parameterize a force field for a system, how long does that usually take? How much effort do you have to put in to do so?
Well, of course, it's a bit like how long is a piece of string. You know, it can take a long time, and you know, that's a scary story. But you know, people have dedicated a whole PhD to getting force fields, but that of course is unusual. I think when my student did it, we were talking of a matter of months, and that was obviously quite a complicated thing to do because we weren't trying to reproduce a structural phase diagram. But I think you wouldn't do it in less than a few months. And it really depends on what's your parameterization, what's your force fields, type of force field you want to parameterize, and what the material is, and how much has been done before. So the question is, there's a lot of force fields out there for many different materials. Is there one similar that you can start with and just modify a little bit? That's what usually happens, actually. Are you thinking of any particular material?
Nothing in particular yet, but maybe for some future research and just out of curiosity.
Yeah, well, obviously you start by looking at what's out there, and is there something close to what you're trying to do, and then you work with that. To start from scratch, absolutely having no idea about, you know, nobody's done anything on it before, is quite challenging. But
thank you.
So what class of material would you be interested in, do you think?
Well, my research is going to be focusing on modeling some TMD and maybe oxygen-water interactions.
Okay.
So, something along the lines of that, possibly.
So you may be thinking of something like the reacts SF type potentials, and there may be things in there that already work. Are you doing DFT? Or are you doing classical potentials at the minute?
No, DFT at the moment.
Yeah, you may find there's something in the literature already, or at least something would be close, because obviously it's a popular system.
Thank you very much. And your talk was very interesting, so thank you.
Thank you. Anybody else doing anything on class, or thinking about doing anything in classical simulations?
Yeah, I mean, We're kind of very similar thing to Daria, and I'm thinking about looking at interfaces. So just for ReactFF, is there like an atom limit, considering it's slightly more complicated than like a bucking potential, which you need to consider?
Sorry, I missed that. Was there an email come through and made a noise? Is there what do you need to consider?
Just the amount of atoms in the system I'll be modeling. If like ReactSF, because it's a slightly more complicated force field and way of actually calculating the system, if that's something I'd need to consider more than if I was doing something with bucking and potential. They're
not as efficient as or something like the Buckingham potential or metal potentials, but it's a lot more efficient than DFT. You're probably order of magnitudes less computationally intensive than DFT. So it's a balance between them. But you know, with the current computational power, you can still do a lot of atoms. You're still talking about probably tens of thousands of atoms. So you could certainly easily do interfaces.
Sorry,
if you're looking for the structure, if you're looking for something dynamic, obviously you need a longer time scales. But first, for your structures, I think things like grain boundaries and surfaces and interfaces are well within the remit of ReactSF potentials.
And then, sorry, I was also wondering as well, what you would choose to model your like fitting of potentials off, because I know you're saying that your group went off DFT calculations. But is there a specific choice where you'd say DFT would be better to do fitting than the actual experimental values?
It depends many experiments you have. And so we used basically DFT because if you couldn't really make, experiments can't make an ordered one of these PZT when you go to 50%. So we can make any structure you want in DFT, and that often happens. So you can use hypothetical structures. I think when I showed in the recordings, silicon, a lot of the structures just don't exist experimentally. So you can explore things that are hypothetical structures. It's obviously good if you can, other properties such as elastic properties can be well, experimentally characterized, but quite often you want to do structures that don't actually exist. So if you can fit to lots of different structures, I think DFT is a good choice.
Okay, great. Thank you very much.
Anybody else, any comments or questions? So I think you'll hear more about fitting. I'm not a fitting expert, so you'll hear more about fitting next week. It's quite, and maybe using machine learning. Machine learning seems to be getting more and more popular. I think, as I commented before, that it's basically you do lose a little bit in terms of the understanding of the physics. You're effectively working with lots and lots of numbers. You lose the understanding, but underlying understanding. But they are quite effective and more efficient than DFT again. Any other comments? So are you all from UCL or are you different universities? I find it quite difficult to do this sort of type of tutorial when you can't actually see and hear everybody at the same time. So it's harder to actually interact. Okay, no other questions or comments? We'll just no hands. We'll let you go, and good luck with your PhDs, and I hope you get back to face-to-face contact soon. Okay. Oh, I got a hand. Okay. Bye.
Thank you.
Thank you.
Bye.
Bye.
Thank you very much.
Thank you.
Yes.
Thank you. Bye.
Thanks for coming.